Tonight, a dead star might explode 10 trillion years from now. It sounds insane, but black dwarf supernovae are a real prediction. The immediate takeaway is this: the future will not be quiet. Instead, the cosmos whispers for ages, and whispers decide endings. Think beyond galaxy smash-ups and tired heat-death headlines from textbooks. We are chasing subtle engines that steer fate, slowly but relentlessly. They hide in cold dwarfs, fading particles, and the vacuum itself. Tiny effects can outvote fireworks, given ridiculous time on the clock, so we will zoom in and watch the quiet levers move. By the end, the future feels stranger, but more understandable. In the far darkness, white dwarfs cool into black dwarfs. A black dwarf is a dead star core, chilled near absolute zero. That matters because chemistry freezes, and fusion seems permanently impossible. But iron nuclei inside can still capture electrons, changing elements atom by atom. Each capture nudges pressure and packs the core even tighter. Over absurd timescales, pycnonuclear fusion ignites from sheer compression. No heat spark is needed, just crushing density in a lattice. Mechanically, the core reaches runaway conditions and a supernova triggers again. Suddenly, a corpse star flashes, after 10 to the power of 110 years. That number dwarfs proton lifetimes and everything else we know. Example in real terms, consider a one solar mass carbon dwarf. It cools for eons, crystallizes, and slowly builds electron captures inside. Eventually, central density passes a threshold, and fusion avalanches through. The result mimics a type Ia supernova, but without fresh accretion. Astronomer Matt Kaplan proposed this pathway, with breathtaking wait times. It is speculative, yet it obeys known nuclear physics. Rule of thumb: if densities climb, quantum tunneling finds a route. Multiply that across countless remnants and flashes will pepper the darkness. Not many per galaxy, but non-zero across absurd gulfs of time. So the heat-death picture gets speckled by these delayed eruptions. Energy still escapes, information still spreads, and structures keep relaxing. Bottom line, dead stars can still vote if you wait long enough. Walk into a stellar graveyard and the floor crunches like ice. White dwarf crystallization is ions freezing into a solid lattice. It matters because cooling stalls, and galaxies fade more slowly overall. Inside, carbon and oxygen ions lock together, squeezing out impurities. That squeeze releases latent heat, which props up the luminosity temporarily. Heavier oxygen sinks inward, separating from carbon and releasing gravitational energy. The star shines longer than expected, so our cosmic clocks shift. Astronomers saw a pileup of white dwarfs at specific brightnesses. Gaia mapped that kink, confirming crystallization in real populations. Example numbers help here. Hundreds of millions show the same slowdown. Extend that effect forward and star graveyards glow for longer epochs. That glow feeds any lingering planets and warms drifting comets slightly. Energy budgets decide chemistry, survival, and evaporation across dark eras. Common mistake is thinking dead means inert, but phase changes work. Crystals crawl across the core, and the brightness curve flattens. That flattening compounds across billions of corpses, tilting galaxy light histories. This anchors stellar chronometers, which measure ages in cooling time. Calibrated clocks matter for fate because rates decide future fuel. Stars end feeding black holes, winds, and interstellar chemistry on schedule. So the picture is simple: crystals slow the night's dimming. Across time, that delay changes merger remnants and halo heating. It nudges how fast galaxies relax after their last bright stars. What to remember: frozen cores by the universe extra twilight. Bottom line, slow crystallization bends timelines with quiet, measurable physics. There is matter we never see, yet it sculpts every galaxy. Dark matter is invisible mass that binds halos with gravity. It can also leak energy through annihilation or very slow decay. That matters because halo gas cools, forms stars, or stays hot. A tiny heating trickle can tip those choices for eons. When particles annihilate, the rate scales with density squared. More crowded cores get more heating, while outskirts get less. If particles decay, the rate depends on lifetime and density. Either way, energy becomes fast electrons, photons, and slight ionization. That slows cooling flows, changes pressure support, and delays star births. Dwarf galaxies feel this most because their wells are shallow. A trickle there can halt clouds and keep gas puffy and stable. Numbers help sanity check. Lifetimes beyond 10 to the power of 26 seconds still matter. That is longer than the universe, yet cumulative heating accrues. Rule of thumb, density cores magnify annihilation, while decay stays uniform. Simulations show altered gas temperatures by a few thousand Kelvin. Multiply that across cosmic time and star histories diverge substantially. We can test hints in dwarfs, clusters, and the background glow. Radio and gamma maps already impose limits, but not ruling out everything. So the picture is sobering. Hidden heat could set the thermostat. If dark matter warms halos, tomorrow's stars may never ignite. Bottom line, unseen particles might throttle the universe's remaining fuel. Far from any star, a black hole whispers with heat. Hawking radiation means black holes emit light and slowly lose mass. It matters because in deep futures, only these embers remain. Temperature rises as mass drops, so small holes glow much hotter. Big holes are cold, while tiny ones fizz like kettles. Quantum pairs near the horizon separate, stealing energy from the whole. Over time, the mass shrinks until a violent final flash. One solar mass evaporates after about 10 to the power of 64 years. A mountain mass goes sooner, within 10 to the power of 52 years. Asteroid mass remnants could pop within cosmological dark ages. If primordial black holes formed small, some might be ending now. Gamma flashes would mark them, but surveys have tight constraints. Gravitational waves also carry hints from early mergers and dynamics. Example estimate, final seconds release about 1 to 10 megatons equivalent, not galaxy-shattering, but noticeable against a silent cosmic background. So the picture is elegant. Black holes end with tiny fireworks. Those sparks still move energy outward and smooth remaining gradients. Smoothing is the universe's hobby, and Hawking glow helps finish. Rule of thumb, lighter means louder for this quantum hiss. We build detectors now to cage whispers from the abyss. If nothing appears, limits still tighten and theories get cleaner. Bottom line, the last lights are small, steady, and final. Imagine a granite boulder hissing once every unimaginable century. That hiss is hypothetical proton decay, a particle blinking out. It matters because if protons die, matter itself dissolves. Atoms would crumble, molecules would fail, and planets would erode. In some grand unifications, protons decay with absurd longevity. Current limits exceed 10 to the power of 34 years for favored channels. That is beyond stars, galaxies, and modern detector patience by far. Mechanically, heavy bosons mediate quark swaps, creating positrons and pions. Bound nucleons complicate rates, but dissolution still marches eventually. Each decay releases energy, warming remnants with rare tiny sparks. Example scale, a kilogram would lose a few atoms each millennium. Across a galaxy, those pinpricks still add heat to nothingness. Experiments like Super Kamiokins stare at water, chasing impossible flashes. No events yet, which pushes lifetimes longer and longer again. Common mistake is assuming false means useless, but bounds reshape models. If protons never decay, structures persist and black holes dominate. If they do, chemistry ends and dust fades into radiation. So the stakes extend everywhere, from pebbles to galaxy cores. Bottom line, proton fate chooses the universe's final background texture. Watch the debris field grow, one faint particle at a time. Over eons, the debris wins and solid shapes evaporate. Stretch a hand into emptiness and you touch a loaded spring. Vacuum metastability means space might sit in a false minimum. It matters because a quantum jump could rewrite every constant instantly. A true vacuum bubble could appear and race outward near light. Inside the bubble, particles behave differently and atoms cannot form. In quantum terms, fields tunnel through an energy barrier without a classical push. The wall harvests vacuum energy and expands with titanic efficiency. No warning exists because signals cannot outrun the advancing boundary. Calculations using the Higgs suggest lifetimes vastly longer than everything. Add unknown high-energy physics and stability may be completely safe. Example probabilities drop like double exponentials beyond human or stellar scales. Common mistake is treating this like a doomsday warning. It is not. Instead, it shows empty space has structure and that structure matters. Bottom line, vacuum character quietly sets whether forever actually continues. If the bubble never comes, cosmic cooling proceeds without interruption. If it does, the story ends cleanly and immediately. So the stakes are binary but still shape today's theories. Physicists use stability to constrain couplings and guide collider searches. That feedback circles back, informing cosmology and early inflation models. Net result, checking the vacuum now clarifies the path far ahead. Two dead stars dance in darkness, and the music leaks away. Gravitational waves are ripples that carry orbital energy into space. It matters because leaking energy shrinks orbits, and collisions follow. Mechanically, any quadrupole motion radiates, and the power rises steeply. Tighter binaries lose more energy, which tightens them even faster. Encounters in clusters harden pairs, while slingshots eject wanderers. Ejected objects heat halos and slowly puff out galaxy centers. Mergers seed bigger black holes, which then reshape orbits around them. Each merger launches a recoil, scattering nearby stars and gas. Example numbers: LIGO sees dozens yearly from only recent universe. Stretch that rate across trillions of years, and remnants dominate. Compact binaries keep merging until black holes hoard the remaining mass. Their wave background adds steady drag, like syrup on orbital gears. Common mistake is thinking waves only matter during the crash. They matter earlier, deciding which pairs survive and which evaporate. Bottom line, quiet radiation writes the merger schedule for eternity. So those whispers are not fluff, they are the steering wheel. Dead stars may explode again, particles may warm the dark. Black holes hiss away, and gravity scribbles in wave lines. Vacuum itself holds a verdict on whether forever keeps going. The big moves grab headlines, but the small moves accumulate. Net result, tomorrow's universe is written by patient, overlooked processes. If this changed how you picture eternity, stick around for more. I post deep dives like this, always clear and curiosity first. Tap subscribe and join the hunt for quiet cosmic levers. Those black dwarf sparks were the hook, and they still haunt.